All right, guys, so this is going to be the spectral analysis lab. So basically the point of this lab is to use what we know about diffraction and what we know about the hydrogen atom in order to solve for something called the Rydberg constant. Okay, and so we'll see how all of these things are connected and exactly what the Rydberg constant is. But before we do that, let's just kind of review some important information about diffraction. So let's say we have some light source here, right, and it's shining some light. Let's say that this is just red, just has one wavelength. It's one single wavelength of light, right? And we're going to pass this through a diffraction grating, which has some groove density, some number of grooves per unit length. Okay. If we then view the light on some viewing screen some distance away, what we'll see is a diffraction pattern, right? So this should all look hopefully very familiar to you. So we'll have these varying diffraction orders. Looks something like that, right? Where this central maxima has a diffraction order of 0, right? And then these two on either side, closest to the central maxima, have a diffraction order of 1, and then the next two after that would have a diffraction order of 2, and so on, right? This continues to go on. But you can see each of these has a differing intensity. So the central maxima will be the most intense, and then as we go further and further away from the central maxima, the light will become less and less bright. Okay, and then we have these regions of interference in between where we have no light. So the equation, as you hopefully remember, that kind of relates the geometry of this system to these diffraction orders and to the wavelength of this in this case red light is going to be the diffraction equation, which looks like this: d sine theta, where m is this diffraction order, lambda is the wavelength of the light that we're talking about, d is the spacing of the grooves on our diffraction grating. And then lambda is going to be the angle between the central maxima and then whatever corresponding maxima we're talking about. So for instance, for m equals 1 here, the angle theta that we're talking about there is this angle here. Okay, but we could also talk about this angle theta, which goes to m2, right? So it's basically this angle theta is a measurement of how far away from my central maximum I am. So this is the case for a single wavelength, right? You can see that this equation for diffraction depends on the wavelength of our light. So let's say that our source is emitting different colors of light, okay? What we'll see is the higher wavelength. So for instance, red light has a very high wavelength, which means the separation of these peaks will be very large. Whereas something like blue or violet light has a very small wavelength, and so the separation of these M1, M2, and so on peaks away from the central maxima will be much smaller, right? So we can use this fact that the spacing is different in order to separate the light coming from a source that has multiple colors in it. We can use this to separate it into its components. And this is what we call a spectra. So if we, instead of just red light here, if this was filled with hydrogen, and if we excite hydrogen, the electrons in hydrogen, it turns out that we can get a number of different colors or a number of different photons can be emitted, each of them having a different wavelength, right? And this number will be unique to hydrogen, or these colors will be unique to hydrogen. So if we look at the spectra of, again, any element, or of, say, hydrogen, it will be unique to that element. So it's a way of identifying our materials. So let's talk about this, how hydrogen can emit multiple wavelengths a little bit further. So if we have a really simplistic drawing of a hydrogen nucleus there, and we have these different orbitals where the electron can be located, right? Something like that. This closest will have atomic number equal to 1, or a quantum number equal to 1, or orbital, the first orbital. And then the second orbital will have an n equal to 2. This third orbital will have an n equal to 3, and so on, right? So this will be 4, and then this will be 5. N is equal to 5. All right, so initially our electron, because we're talking about hydrogen, is located in our ground state here. So we only have a single electron in our ground state. And now, if this electron is then excited, let's say by heating the hydrogen up, in the case of a light bulb filled with hydrogen, if we excite it, it can be excited to any number of these energy levels. So there's one case where the electron jumps all the way up to n equals 5, there's one case where it goes to 4, and there's one case where it goes to 3, and it could also go to 2 and so forth, right? And then once these electrons get excited, they'll fall back down and they'll emit a photon. Okay, and what we were going to talk about specifically here is only the case where these electrons fall down and emit a photon that is in the visible range, right? And this is called a Balmer series. All right, that just means that whenever it falls back down, it emits a photon that's visible. And for hydrogen, that means that it's falling to this second order, n equals 2. So all of these transitions, 5 to 2, 4 to 2, 3 to 2, and then 6 to 2, I just haven't drawn. All of those emissions will result in a photon. So a photon comes out after this electron falls, and it'll emit a photon that's equal to the energy difference between this n equals 5 level and the n equals 2 level. So this is how a hydrogen atom is able to emit energy in different wavelengths, right? It depends on where is my electron being excited to, and when it falls, and specifically for the Balmer series, when it falls to the second level, it emits a photon that we can then see. Right? If this electron, instead of falling to 2, had fallen to 1, so if it goes from 5 to 1, it's actually going to be, it'll actually emit a UV ray, and this is something different to a Balmer series. And then if it, instead of going to 2, instead of it goes from like 5 to 4, it'll emit a photon in the infrared because it has a much less energy. Okay, so these are by all means not the only transitions that can happen, but they're the only transitions that we care about because they're the ones that we can directly measure and that we can actually visualize. So those are the ones that we'll be talking about today. So because these electrons are always falling to the second level, we'll say that for a Balmer series, our final energy level is always equal to 2. This is specific for Balmer. Okay, and now in the case of hydrogen, if our initial, so if it starts in the 6th energy orbital, which I don't have drawn here, but you can imagine it being there. If it starts in 6 and then falls to 2, because 2 is always our final, then the photon that will be emitted will be violet. All right, and then if it starts instead in 5, it gets excited to 5 and then again falls to 2, we'll get another photon that is also violet, but a different shade of violet. If it starts in 4 and emits a photon by dropping down to 2, we'll get cyan. And then the final transition for the Balmer series is going from 3 to 2, in which case we'll get some red light. So when we're looking at the visible spectra of hydrogen, this is what we should see. We should see violet, violet, cyan, red if we're looking across this screen here, right? Because it'll be violet first because that means the spacing between these maxima is smallest. So if we're going from the central maximum and viewing going across the screen, we'll see M1 peak that corresponds to violet first. Then we'll see an M1 peak that corresponds to this violet. So we'll see 2 violet bands. And then as we keep coming across, we'll see an N1 for cyan, and then we'll see the M1 for red. M, not N, if that was clear. So we'll see the first order diffraction for each of these colors in this order. And then as we keep coming down, once we hit this where we're able to, once we pass all of the first order diffractions, then we'll again see these colors in this order, but this will be the second order diffraction. So we'll see violet, violet, cyan, red in that order again, but that will be corresponding to the second order diffraction if we're just looking along this viewing screen. Now, we can go the opposite direction as well, and it's the same thing. We're just looking, instead of looking on this side of our maximum, we're going to be looking on that side of the maximum. So we can go in either direction. But we'll see the same thing going in either direction, right? Because this is also just the first order diffraction order. So we'll see going again after the principal maxima, we'll see violet, violet, cyan, red in that order. And between each of those colors will be an area of black where there's nothing. There's no light. And then we'll see after the red for the first order diffraction, then we'll see again violet, violet, cyan, red in this same order, right? So hopefully you get the idea of what we're doing. So what we're going to be doing is shining a hydrogen light source through a diffraction grating, and then we'll be able to see the positions of all of these different peaks, okay? And then we can measure the angle corresponding to those different peaks. So the table that you end up getting will look something like this. We're going down here. We have our initial energy levels, right? Where this one is violet. This one is also violet. This one would correspond to cyan, and then this one will correspond to red, right? And then going across this way, we'll have our diffraction order. So we'll have two going one in one direction and the other in the other direction. So we'll have two first order diffractions like this one and this one. Then we'll have two second order diffractions, this one, and then two third order diffractions, which I don't have drawn here, but you can imagine there just being another peak further out on either side, right? And so at each of these diffraction orders, for each of these colors, you'll be able to measure this angle, right? This angle theta that goes to that diffraction order for that specific color. So we'll have angles populating all of this going across this way, going across that way, and then of course filling this whole table out with angles. And then from these angles, right, what we'll calculate is an average lambda average. So going across this top, we can calculate the lambda for each of these diffraction orders for this color using our diffraction equation right here, and then using the angle that we measure, that we're going to be measuring. And D is going to be given, M is the diffraction order given here, given up here. And then we'll be able to calculate lambda for all of these, we'll be able to calculate lambda for all of these blanks or for all of these positions in this table, and then we can average the lambdas in this column over here for violet. So we'll get an average or experimental value for the wavelength that corresponds to this energy level. Okay, and we'll do the same thing for each of these. So we'll end up getting 4 average values for the wavelength that correspond to these 4 different initial energy values. And what we're going to do with that is use them to then calculate something called the Rydberg constant. All right, so the Rydberg constant is something that relates these wavelengths to our initial and our final energies in the Balmer series, specifically for hydrogen. Okay, so this equation looks something like this, where we have 1 over our wavelength is equal to the Rydberg constant, which is just R sub H because it's the hydrogen Rydberg constant. And then we have in parentheses the final energy level squared minus the initial energy level squared. Okay, so we can take these wavelengths here and then plug them into here, and be able to, and using the fact that we know NF is 2, and then knowing that NI for each of these wavelengths is 6 for the violet wavelength, 5 for this second violet wavelength, NI would be 4 for this cyan wavelength, and then it would be 3 for whatever this red wavelength ends up being. We can use that information to then find out what this RH is by graphing it, okay, and then finding the slope. So if we set 1 over lambda as our y, Let's rewrite this right-hand side to be a little bit easier to see what's happening. So we'll just distribute the Rydberg constant, and this would be minus RH 1 over Ni squared, right? That means this is my B, this would be my X, because I can vary, NF is constant, it's always 2, so you could really rewrite this as NH over 4. You don't have to write the NF. And then this would be my slope, M. All right, so let's see what this graph will look like when we graph it. So on our Y, we have the 1 over Y. On our X, we have our 1 over Ni squared. And then we can see that the slope of this line will be negative, and then the slope will be equal to the Rydberg constant. All right, so then just taking the slope of this will give us this number here, right? Where NF again is 2 because we're in the Balmer series, because we're in the visible range. So yeah, this is what you'll do. You'll use these angles to calculate these average wavelengths, and then you'll graph 1 over each of those average wavelengths. So we'll only have four data points, right? At each of these four initial energy levels. And then from that slope, we can then determine the Rydberg constant. Now, if you're paying attention, or you might think that, oh, you can also find the Rydberg constant using this y-intercept, and you'd be correct, right? So you can actually find this Rydberg constant in 2 ways. One, by finding the slope that we talked about, or if you find the position, this position that we cross the y-intercept, we also know that y-intercept is going to be equal to RH over 4 because NF is equal to 2, right? So if we get our y-intercept and then multiply it by 4, we can then determine from that also the Rydberg constant. So I suggest you do it both ways and just check that they're both the same to each other, and then also the same to whatever the experimental value or the theoretical value given to you in your manual is. Okay, so this is spectral analysis. So what you'll see me doing next is going over in lab, going over how are we going to actually determine these angles that we can then use to calculate this average wavelength for each of these initial energy levels. Okay. Okay guys, here we are in lab. So this will be for the spectral analysis. So you can see here, this is our light source. Within this tube is helium. And then if we flick this on using this bottom switch down here, you can see that starts to light up. And then within this helium, right, are many different wavelengths of light. And we'll be able to see those here in a second. But anyways, the light will pass through this aperture here, go all the way through this lens, and then here is our diffraction grating. So if we look at that diffraction grating, you can see that it says 300 lines per millimeter. So that tells you something about the density of the grooves in that diffraction grating. Okay, so from that, we could be able to determine what the groove distance is. All right, over here is our viewing microscope. So we'll be able to rotate this, you can see, and then as the light passes through this diffraction grating, it'll get diffracted at multiple different angles. And to view each of those diffraction orders, we can then rotate this to view them to either side, right? And to measure the angle, let's say we've rotated this all the way over here, and we want to measure that angle, we can look into here, and then there's a goniometer, okay? And then you can see where that 0 is. We want to see where is that lined up inside of this main scale here. So this is very similar to a vernier caliper, right? And so from this, we'll be able to record what the angle, this angle here is. All right, so what I'll do next is we'll get this back so we're lined up with m equals 0. M equals 0 is shared by all of the wavelengths. So it'll be whatever the color of that helium lamp is, that'll be our m equals 0. And then we'll rotate to either side and be able to see all of those different diffraction orders, right? We should see violet, cyan, and then red, okay? One other thing in this setup is we have this cloth that we can place over our setup to get rid of any ambient light. So as we're rotating, we'll make sure that we have that over the diffraction grating to prevent any ambient light from getting into the system. Okay, so what I'm going to try to do now is I'm going to turn the light off. We'll get you lined up with this nozzle or with this eyepiece, and then we'll rotate to either side so you can hopefully be able to see those diffraction orders. Okay guys, here we are looking through the eyepiece. We're currently lined up with that m equals 0. That m equals 0 diffraction order. You can see it's the same color as what the hydrogen lamp was, because all of the diffraction orders share the same central peak. Now if we start to rotate counterclockwise, we will hopefully be able to see, you can see that there's, if we come over, you can see that there's a violet there. It's kind of hard to make out on this camera, but there's a violet there. There's our cyan. And as we continue to rotate, there's our red. So that's the first diffraction order, m equals 1, for each of those colors. Now if we keep coming over, I passed it. Yeah, so there's the diffraction order 1 for red. If we keep coming over, we can see there's violet 1, violet 2, cyan, and then where are we? We're missing red. There's red in there. Yeah, sorry, it's hard to see using my phone, guys. Yeah. So yeah, this is about as good as we're going to be able to get. So we are just looking through that eyepiece. But you could at least hopefully make out some of those spectral lines, and you'll be able to see how they'll repeat. So as we were coming this way, right? So right there was our m equals 0, and as we rotated, we saw violet, violet, cyan, red, and then as we continue to rotate, we again saw violet, violet, cyan, red, right? So we would see that 3 times going this way, and then what you would have done is just done the same thing, rotating the opposite direction. So we would have come this way, violet, violet, cyan, red, 3 times going that way, measuring this angle from here each time. Okay, and that's what you'll see in your data sheet, is you'll see 3 diffraction orders to either side of, so you'll have 6 diffraction orders in total, and each one of those will correspond to a color, and for each color, you'll get a angle reading here. And then from those angles, again, you'll be able to calculate the wavelength, and then from the wavelength, finally, the Rydberg constant. All right, guys, hopefully that demonstrated well enough what you would have done in lab. Yeah, and you can, find, like I said, find your data on Canvas that you can then use to finish your analysis. All right, guys, so don't forget to like and subscribe, and we will see you next time.